a set of a pi bond, and adjacent an atom which has either lone pairs or an empty orbital. So in this case, we have an empty p orbital, and the way we've drawn it, we took the time last time to draw various representations about this allocation. The simplest, certainly by far the simplest way of drawing it, is to simply say, well, we're going to move the electrons like we're going to draw resonance structures, and we get that kind of a situation. That's the simplest and the easiest way. Now, we keep telling you, reminding you that resonance structures are not real structures, they're just figments of our imagination. The real structure is a composite, and so if you wanted to be a little bit more correct, you could draw a structure like that one. If you wanted to focus a little bit more on it, you'd say we want to draw a structure like that, in which essentially the positive charges are equally distributed at the end. So it's the positive charge on each carbon carries essentially half of a positive charge. And then you could also imagine it in terms of p orbitals, that the two electrons are distributed evenly amongst the three orbitals to make one bond, the equivalent of one bond across. But from a point of mechanism, the top two are the easiest ones to use because it's easier to do the bookkeeping about the bond, making and breaking bonds. The other thing that I wanted to make sure that you sort of appreciate, because of the resonance stabilization, the stability of this cation is at least comparable to that of a tertiary carbocation. It might even, most often, allylic carbocations, especially if they have alpha groups on them, are actually more stable than tertiary carbocations. But at least you've got to recognize that this is comparable to or better than a tertiary carbocation. So that was the first part, and then we went through that last time. And that's a special situation where we have the parent compound, the symmetrical compound, almost invariably. Yes, sir. This is supposed to be a half of a positive charge on this carbon and half on that one. Pardon? This central carbon gets electrons from both sides of the bond, so it doesn't really carry any formal charge. You can't draw a positive charge there, any kind of a positive charge. You cannot attack that central carbon with a nucleophile. So it's kind of a node in the middle of the electron density. So you always attack at the terminus. You never do. And the resonance structures also suggest that positive charge is mainly concentrated on that carbon and on this carbon. When you flip back and forth, the central carbon always seems to have 8 electrons. It's the other ones that are always missing 1, or half the time they're missing 1, so half a positive charge. Okay? All right, no problem. So the reality is that we really deal only rarely with this case. We really deal mostly with unsymmetrical allyl carbocations. That's 99.99% of the time. So we have, again, the pi-allyl system, or the allyl system with a partial bond between all the 3 carbons. But we put substituents on one of them. And you ask yourself, now how do the substituents affect the charge density? And since we agree that methyl groups are electron donating, it certainly suggests that the positive charge, the whole thing carries a positive charge, that the positive charge is more concentrated on that carbon than on that carbon. There's still significant amount of positive charge here, but if anything, more than a half of it is here and less than a half of it is there. And it depends on the nature of the substituents. Electron donating substituents will favor a positive charge here. Electron withdrawing will favor it on the other side, as always. And the other thing, when you have unsymmetrical systems, such as this one here, the nucleophile can attack in principle and in practice on either side. So you can get the nucleophile attacking at the more substituted carbon and at the less substituted carbon. And we'll discuss a little bit as to what you'd expect under certain conditions. And the first thing that you might realistically expect, if this carbon carries most of the positive charge, the nucleophile will be most readily attracted to that carbon. And we'll see that that is in fact the case. So this is going to be the fastest reacting system, fastest reacting place. And we'll eventually call, when we do the data and discuss the ratio of the two possible products, under what condition do you get mostly this, under what condition do you mostly get that, it'll make some sense that the nucleophile prefers most readily to go to that carbon, but that's actually the more stable product. So we'll talk about that, how that arises in a little while. Okay, so that's the properties. The second thing we talked about last time, and I wanted to, it's important to do it again, is to recall or to remember or to be aware of the ways you can generate allyl-cations. The very first example we had in the last lecture was we had a system like this, a leaving group on the carbon adjacent to the pi system. And you ought to be comfortable with the idea that this is the pi system, and the adjacent carbons are called allylic carbons. And so is that one. And the hydrogens, excuse me, these two hydrogens, and these three would also be called allylic hydrogens, and they have special properties. Same thing with allylic carbons, because they are adjacent to the pi system. They can support a positive charge more readily than a typical carbon. They'll also, as we see later, they'll be able to support a radical better. Even a negative charge can be supported better because of the adjacent pi system. So you need to recognize that the allylic position gives special kinds of reactivity because of the conjugation and the resonance effects. So we have a leaving group, the bromine on the allylic carbon. If we react this under SN1 conditions, not a very strong nucleophile, a polar solvent, those are all the things you may remember about SN1 conditions, we get a carbocation, an allylic carbocation, and I'm not going to read, I've already written it many times in the resonance form, there's no point writing it again.